Good afternoon. I am santhiya, Priya, Assistant Professor of Chemistry, JJ College of Arts and Science, Pudukkottai. Today class it will be series Nuclear Chemistry. Nuclear chemistry, some basis for this nuclear chemistry. Yeah, nuclear contains proton, neutrons are bound together by strong nuclear force. The particles in the nucleus are collectively called nucleons. What is nucleons? The particles in the nucleus are collectively is called nucleons. The nucleus is tiny part entire the atom or nucleus, which is 10 power minus 15 meter, or atom is equal to 10 power minus 10 meters. The atom can be symbolized by XAZ or AX. A is the mass number of nucleons, proton plus neutrons. Z is atomic number of protons is protons. The subatomic particles. The nucleus of an atom can undergo decay to produce a new nucleus before or some other possible decay products. The subatomic particles is the proton, 1 and 1, neutrons and 0 1 is the electrons is minus 1 0. Then the like electrons but with the positive charge of this reactions. The other decay product is a gamma ray. The no change, no mass, no charge and no mass, no changes. The high energy electromagnetic radiations. Alpha particles is a helium made up of two protons and two neutrons. These someone name alpha particles. First one alpha particles is a helium 4 2. The 2 4 is a high energy helium nuclei considered in these reactions. Consider these reactions. 4 of two protons and two neutrons. Next one beta particles is high energy electrons. Positron particles it will be the same mass electron but one unit is will be the positive charge. Proton the nuclei of hydrogen atom. Neutron particles with mass extensively equal to the proton with no change. Gamma ray very high energy electromagnetic radiations. Then, other than the nuclear stability of the thousands of nucleates, it exits about the 250 or stable. It will be blue color is 250. We see the blue color. All other are unstables are green color. They see this green color, it will be the unstable. The stable with blue color, unstable with the green color. The graph show neutron proton ratio for this isotope. Light atoms have this ratio 1 is to 1. Large atoms are about 1.5 is to 1. The nuclei have n by z ratio region. Too many neutrons, not young protons. Too many protons, not young neutrons. Too many protons and neutrons. The nuclear, some stable isotope nuclear. The currently known isotope 157 is a even, 153 even odd, 50 odd even, 5 odd. The number of stable isotopes it will be first proton number then neutron number. Most stable isotope have an even number of protons and neutrons. There are slightly more stable isotope with even number of protons and odd number of neutrons. Isotope with the odd number of protons, neutrons are generally or not stable. Radioactive decay process, it will be the nuclei can be unstable, too much mass, energy, etc. For example, then unstable nuclei become stable with radioactive process, conversion of one nuclei into another nuclear transmutation. The radioactivity is the emission of radioactive decay products. Five types of radioactive decays. First one is alpha decay. A particles containing two protons, two neutrons is called the alpha decay process. Protons decay protons is will be radioactive. The example is uranium 92 238 Qs, thorium 90 234, helium 24. They are called nuclear equations. The second one beta electrons is emitted, the atomic number is increased by 1. For example, radiation the 88 to 28, AC 89 to 28. Denote the conversion of mass in P protons is the electron. The positron emission. Next one, positron emission. First one alpha, second one beta, third one positrons. Emission of protons from the nucleus, atomic number is decreased by 1, neutron is gained. Then oxygen, nitrogen, note the conversion of mass. The protons and the neutrons, they will be electrons. Another one, the gamma ray emissions. Emission of gamma radiation, high energy. It will be short wavelength. Protons emitted from excited nuclei with other decay processes. Uranium, thorium, helium is will be conversion process. The emitted most radioactive decay process commonly left over the nuclear equation. Next one, electron capture. The inner electron in an atom captured by the atom nucleus. Proton is converted to neutron. Atomic number decreased by 1 K. E is alkanes. Proton, neutrons will be the electrons. The radioactive decay process will be the alpha, beta, gamma, positrons, electron. It will be short notes on for these reactions. Next one is nuclear binding energy. The energy required to bind the nucleons in a nucleus together. It will be amount of energy per nucleon. Larger binding energy generally meant by more stable nuclei, measured by MeV nucleon. EV is electron volt. MeV will be electron volt. The example for this binding energy of the alpha particles nucleus to 8.4 MeV by 4 nucleons, 7.10 MeV nucleons. Then separating the nucleus requires this energy plus helium nucleus, then to give this constituent nucleons. Binding nucleus will be constituent nucleons to give the helium nucleus plus energy. The mass defect. What is mass defect? Mass nucleus smaller than the masses of its constituent nucleons. The missing mass is called mass defect. Constituent nucleons will be helium nucleons. And the mass defect 0.0305 AMU. Mass in energy. Missing mass of this energy was released when this nucleus are formed. Missing mass nucleus is will be the binding energy. Another then most important for this mass defect. Albert Einstein famous mass energy equivalence equation relates the mass the energy. E is equal to mc squared. E is equal to energy. M is equal to mass. C is equal to speed in light. The nuclear binding energy is directly related to the missing mass. Adding energy increase the mass while reducing energy reduces mass. Two examples. For example, the carbon-16 mass defect 0.1188 AMU. Nuclear binding energies will be the isotope. Determine the number of nucleons P plus N is equal to 16. New nucleons will be 16. Convert the mass 1.66 into 10 power minus 27. The equation is substituted by this values to give E is equal to mc square to give this 1.78 into 10 power minus 1 kg m minus 4 into 11 J mole. So MeV 1 MeV by 1 into 10 power 6 EV to give the 110.87 MeV. To another examples for this reactions to 6.93 MeV for nucleon. The fission. The fission, nuclear fission is splitting a nucleus into smaller component. It will be nuclear fission. So nuclear uranium to give this splitted energy to high for this energy. So for example, uranium, neutron, barium, tritonium, N is equal to give the mc square to give the 2.762 into 10 power minus 1 joule. To another example, 1.66 into 10 power 10 kg mole. To fusion. Fusion process is combining lighter nuclei of heavier nuclei. The result release the enormous amount of energy to give sun undergo fusion reaction 24 by K to produce energy the galactic level. To best example for this flash of sun. Kinetics of radioactive decay. The radioactive decay process follow first order kinetics. The rate law, integrated rate law, half-life periods. To slope of this it will be the half-life periods 5.27 years. The example for 0.32 years minus 1. The another example 1.138. To another example for the solving reaction 29.6 years. The practices for many examples to give the solve these problems to very important portion of this syllabus. Thank you.